Here we have our first STEM presentation for our senior project. We have Braeden here. Braeden is part of the Honors Academies here at Living Word. And what that entails, more or less, is a 3-year process of dozens of hours of assorted work here and there. As part of his commitment to the Academy, he has undergone extra STEM classwork, so more science and more math and more CAD stuff, and we'll see that all bear fruit here soon. We also have a community experience portion, so he has had a number of experiences out in the community, either learning from seminars or attending this or attending that, or just generally being in the STEM field in some sense or other. And finally, the last portion is what he'll be sharing with us today. We have a senior capstone project, and I will leave it to him to tell the details of that, but this will be his presentation, which is his final submission for earning the Academy credit. So, Mr. Christianson, I turn it over to you. Thank you very much.
So first, I'd like to thank you all for coming. As Mr. Schmidt said, my name is Braeden Christianson, and this is my senior capstone project, Beams and Bridges, my introduction to structural engineering. So before we begin with the actual project, I'd like to give an introduction to the STEM Honors Academy just as a concept. So there's a few more requirements, like Mr. Schmidt said, with STEM credits. So it requires me to take at least 2 AP courses in STEM. I'm taking both this year in AP Calculus and AP Statistics. And then 2 additional STEM credits, I believe, a year. So I took Pre-Calculus, Physics, Honors Algebra 2, Computer-Aided Drafting, both last year and then first semester this year, Astronomy, Intro to Computer Science, and Geometry. As well as each year, we have to participate in 2 Academy-approved events. So I mainly do job shadows and other STEM events. And then this, what you're all here for, the Senior Capstone Project. So, the problem. I own a 4-wheeler, which normally is not a problem, but you also need a place to store it. And the place that we have to store it is inside a shed at my house. But the only problem with that is that there is a decent gap between the shed door and the ground, which makes it pretty much impossible to get inside. So there's about a 10-inch gap from the bottom of the shed door from the gravel pad, which does not allow you to drive right up to it. And also the gravel pad next to it has to be able to store a trailer. So any way that I can get the 4-wheeler in there has to be removable to allow storage for the trailer. And there's not even just enough room there to build this simple ramp. Again, for the reasons that it has to be removable, and there's just not enough room there in the first place. Also, I am not able to just raise the gravel pad because of problems with the surrounding grade, and there just would not be enough room for storage. So again, any solution has to be removable because it has to allow for storage of the trailer. And another detail is I took all these dimensions for both the distance from the shed door to the ground, the wood blocking right here to the ground, and then the door width and length all in fall of last year, so I never had to go and remeasure it in the middle of winter. So my solution to this problem is lots and lots and lots and lots and lots of math. So essentially an over-engineered bridge. So the parameters for this bridge, it has to span the entire 118 inches from the wood blocking to the shed door, and it has to carry about 1,400 pounds. That load being the 4-wheeler plus about a passenger. I calculated that by getting the weight of the 4-wheeler, it's about 740 pounds, plus a passenger of roughly 200 pounds, and then multiplying that by a safety factor of 1.5 to get roughly 1,400. So on to the other parameters. The bridge has to be within my own abilities to create, because if I can't make it, it's not really a solution. Second, it has to support the weight requirements, because if I can make it, but it doesn't do anything, then it's kind of useless. Third, it has to be removable and therefore lightweight, so weight is definitely something we're going to be trying to cut down later. And fourth, it has to be at least cost efficient or cost sensitive. So moving on to my materials. So for the bridge, the 2 materials that I really considered were both wood and steel. It was pretty easy choice between the 2. Wood is much lighter, wood is much cheaper, it's a lot easier for me to use, and is much easier to acquire. The difference between steel is that it is stronger and is heavier and is subject to corrosion. So again, bottom line, I don't know how to weld, so steel was out of the picture pretty quick. But another note about the wood is that I'm using pressure treated lumber, because wood itself is not inherently resistant to any environmental damage. So what pressure treated lumber is it uses chemicals that are stronger than those that you can buy in the store, like a sealer or anything, and does that through a pressure treated process. Another note about the wood type is I use southern pine because it is one of the most common in construction. So next, the fun part, all the math. So I did all the math according to ASCE 7, which stands for the American Society of Civil Engineers. So it's just one of their codes. And the way I'm starting to look at this bridge now is by looking at it as, instead of a bridge, as more of a set of beams. It's because of the weight requirements and both just how long they are and the materials I'm using, they are very similar to a beam you'd find in your house. So the way I'm going to calculate that is by first looking at tributary width and loads, how you even define what a load is in this case. And then the 3 different checks I'm looking for in each beam, which is going to be checking the deflection of the wood, the bending strength, and the shear strength of each joist. So first, looking at the loads. So the way we calculate loads for beams is we measure it in pounds per linear foot, or basically you take the tributary width, or the width that the beam is accounting for, times the pounds per square foot of any given load. So what this does is allows the joist to receive an equal load for each foot that it covers. And then what tributary width is, it's measured from the midpoint of the distance in between each joist to the other midpoint. It's basically the width that each joist is accounting for. So, onto the math. First thing that we do is the deflection. So this one was the most likely to fail, I found in most of my tests. And what deflection is how much the beam will visibly bend down. So this is the original position of the beam, and this is it under a load. So it's how much you'll visibly be able to see it bend. So the way you find the maximum allowable, according to ASCE 7, is the length of the bridge divided by 360. And then you'll get the distance of that, and to find the actual deflection under a given load, which is what we need to test for, is this long equation, which I do have referenced as equation number 1 on page 6. So there's a bunch of different variables in it. A couple that will be recurring is W, which is our live plus dead loads, which is live load being the four-wheeler and me, dead load is being the weight of the bridge and the weight of the joist. So L is going to be our length just in feet. It's going to be 118 inches, so about 9.83 feet. E is our modulus of elasticity for the specific wood type. So the way we find that is by looking through essentially a really large spreadsheet, which is called the National Design Specifications Supplement. It's essentially a long spreadsheet of a bunch of different wood types and a bunch of different characteristics of those wood types. So our modulus elasticity for southern pine is 1.6 times 10 to the 6th PSI. And our last variable in this equation is I, or moment of inertia of our cross section. So it's going to be moment of inertia of our rectangle, the cross section of the beam. It's one of the geometric properties of just a rectangle. So the way we then calculate if this actually will stand up is by comparing our maximum, which we found in the first equation, making sure it is either greater than or equal to the actual deflection, which we found our second. So assuming it passed that test, we can go on to the next one, which is our bending strength. So while deflection is more of a visible test that you can actually see, bending strength is the actual strength behind it. So as you can see right here, it's a force that's going to be applied to the middle, and it's going to be applying compression to the top of the joist and tension to the bottom of it. So the way we find the actual strength of one of our members is by finding F prime of B, which is the allowable bending strength of any member. And the way we do that is by looking up our F of B, which is our base value for each wood type, again found in that big spreadsheet, the NDS supplement. And we have to multiply it by a bunch of different factors depending on how we're using that specific piece of wood. So the two that I had to account for is the size factor and the moisture factor, so C sub F and C sub M. For the size factor, it accounts for each different wood size, so that'd be a 2x6, 2x4, 2x8, 2x10. In my literature review, I accounted for both 2x4s and 2x6s because those were the joists I was accounting for when writing it, but all of the calculations I actually did only accounted for 2x6s just because they were much easier to use. So Our size factor for 2x6s is 1.3. Then our moisture factor, given that the bridge is going to be outside and exposed to the elements, we had to account for moisture, so that we multiplying that base value by 0.85. So combining all those together, we can get our F prime of B, or our allowable bending strength, of 1,657 psi for our 2x6. So part 2 of this is finding the actual bending stress. So we found the maximum, now we can find the actual stress on our member. The way we do that is by finding the maximum bending moment first. So that's going to be more of a torque on the middle of the member. The way we do that is by putting our load times our length squared all over 8. And what that does is it finds the torque in foot-pounds, and then plugging that into our second equation, it finds the actual bending stress, which we can then compare to our first one. So all you do is put the maximum bending moment over the section modulus being another geometric property of a cross-section. So that will find our actual bending stress. Then with that, we just compare what we found on the last slide, our F prime of B, which is our maximum bending strength, to our actual stress that we found. As long as the strength is greater than or equal to the actual stress, then it passes the test. So our last one is just shear stress. It's very similar in how we actually calculate it to the bending strength, or the bending stress. And this one was the least likely to fail, because if you think about it, a shear stress is the wood just shearing off as opposed to snapping from bending. So the shear stress was least likely to fail. So again, we find our F prime of V, which is our allowable shear strength, from the NDS supplement. We find the F sub V, excuse me, and then we multiply by our C factors. For our C factors for our shear strength, we only have to account for the moisture factor. So given that, we find our F prime of V, sub V of 169.75 psi for our 2x6s. And then we have to find the actual shear strength, shear stress. Again, we have to find the maximum shear that will be applied to each end as opposed to the middle, like the bending stress. And that is our load times length all over 2. And then we put that times 1.5 over A, where A is the area of our cross section. So once we plug all those numbers in, we can find the actual shear stress and compare it to the number we just found, our F prime sub V. And as long as the allowable over there is greater than or equal to this actual, then it passes the test. So, given all that, I plug all those equations into a very fancy spreadsheet, where I will show you now. So it basically has just a bunch of different variables where you can change the bridge length, you can change the F prime sub B and F prime sub V if they're using different sizes. I never had to switch that because, like I said before, I'm only using 2x6s in any tester equations that I actually did. I can change the lengths, and then I can change the load factors. I never had to change the loads. Well, I did have to change the loads for 2 separate bridges, but we'll get to that in a little bit. And then I have the test that I had to pass on the bottom here, as well as I had a little calculator for a rough weight of the bridges, which will come in just a little bit. Okay, so now that we have a basis for the math and a way to easily change everything, I can start making drafts. So my first draft was just about as basic as I can get. I just covered the entire length, all 6 feet, the entire length, put as many joists as I felt like, so it just looks like a bridge. That's the most basic of designs. So what I did is I took it into Fusion 360, a CAD software I learned first semester this year, and I was able to model this bridge. So you can see from the weight calculator I had each section, so the bridge is split in half to make it easier to carry, is 164.43 pounds. So again, this is just one of the most easiest, most simplest design I could think of, but that doesn't mean it really maximizes anything. So, and the next one I did is I equally spaced the joists out, because what that does is it evens out the tributary width. As you can see here, by evening out the tributary width, or how much load each joist is taking, it evens out the load on each joist, which makes it a lot easier to distribute the weight. So in our first design, I had an middle joist taking up a lot more of the load, that's 35 pounds per linear foot, as opposed to each of the outside ones were only taking 17. So the inside one was taking about twice as much as the outside ones were, as opposed to the second design where you even it out and it cuts down the average load. So uniform tributary width will get you a lot less stress on each individual member. But I went even further than that, because even though the tributary width and the load is distributed over all of them, we're not actually even maximizing any of the properties of the wood yet. So what I did for each of these was I found the unity ratio of each of the properties, where I take the maximum allowable that we found and divided it by I divided the actual stress that we found, that I calculated, and divided it by the maximum, which got a unity ratio, which showed how much of the maximum strength we're actually using. And in this design that has 3 joists, we're only using about 54% of the maximum deflection that we could, and only 32% of the actual bending strength. So there's a lot more strength in the wood that we're not using, and we're just adding to the weight with. So what I did with that was I cut out an entire joist, and it maximized a lot more of the strength for both the bending, shear, and deflection. So we're using a lot more of it now, but it also saved about 20 pounds. Going even further than that, the bridge doesn't actually have to cover the entire span, it just has to be able to get the 4-wheeler across it. So as long as there's room enough for both tires, I can cut out a bunch of the decking, which is one of the biggest contributors of weight. So in addition to the 20 pounds I just saved by cutting a joist out of each of them, I also saved 35 pounds by cutting the decking by an entire foot. So this was the final design that I picked. It uses about 77% of our maximum deflection and about 50% of our maximum bending strength, which isn't ideal, but it was the best I could come up with what I had. So it also only weighs about 110 pounds per each bridge section, which was a big difference from the about 160 pounds original. So finally, we got to the construction. This was honestly one of the more simpler parts after doing all the math and all the 3D modeling, so I already know what it looks like. Having done all that work, this was kind of just our victory lap of having a lot of fun with the project. So this is one of the most fun parts. So on the far left was all the wood minus the decking. In the middle was all the decking. Essentially, it was just a really tedious process of cutting about 42 sections of 2-foot decking over and over again. But here I have the joist connected with bracing, which I did not 3D model because I did not consider it until I actually started building it. And then here's one of the bridge sections complete, and here are both of them complete. So next, one thing I didn't originally account for in the calculations was supports on each side. But what I did was I buried a 4x4 on both the door side and the near side that the bridge will rest on. It doesn't have any effect on any of the math because the load is just spread into the ground from there. So it doesn't have any effect on the math, it's just what the bridge is physically sitting on each side. In addition, it allows the trailer to be stored by itself. It allows the trailer to be stored in there without being anywhere near to it. So final test, it does actually work. I have the 4-wheeler on it, and it is, by definition, a bridge. It is off the ground, not by a lot, but it is still off the ground. So from that, I was also able to calculate measure the actual deflection under load, which is about 1/3 of an inch, which is slightly more than I calculated, but that's just gonna happen, I guess. I'm not very good at structural engineering. And then again, because of all the 3D modeling I did, I was able to only buy the materials that I really needed. So on the left is all the scrap from everything I had. So it's just a couple shavings off of the joists, and then the decking was slightly too wide, so I had to cut some of that off. And then otherwise the middle, you can see the deck is perfectly level. And then again, by definition, a bridge, even if it is only a couple inches off the ground. So my conclusions. Was this a little over-engineered? Maybe, but that's all the point of it. It was really fun learning and applying all the STEM knowledge through all my past 3-4 years in high school to this one project. So I did apply pretty much all of algebra and just doing complex equations like that. And then CAD, being able to model all of them and seeing something actually go from a CAD model to something in real life was really cool and something I hadn't done before. And then again, it was just a fun process learning structural engineering, or basic structural engineering in itself. And I definitely enjoyed the experience. So, here are my references. Anyone have any questions?
Thank you very much. Any of our panel members have a thought or a question? We'll certainly take those. Keenan Gower, you guys are certainly welcome to ask anything that comes to your mind too, by all means.
So I was looking at the equation on page 6, and I was on your slide that said you use feet, but in one of the lower categories it said inches squared. Did you have to convert at all for those?
Or was it
It was
this
last,
one?
Yeah, that one.
Yeah.
So
the one on
yeah,
top.
length is in feet, but the moment of inertia is in like inches, like
Yes,
squared.
correct.
Is that
Actually, yes.
something
So
you have to account for?
yes, in the spreadsheet, I did put it in as feet, but I had the equation calculated from, or converted from feet to inches. So yes, I did account for that in the spreadsheet.
What did you use for fasteners for the top decks to your stringers?
I used just wood screws, or just typical wood screws. I had 2 on each joist. I'll go back to it. Yeah, I don't think you can really see it, but I did 2 on each side for each decking board.
Is there a calculation for deflection of how many fasteners you use in a joist?
I did not.
May have added to your deflection?
That's an excellent question. I did not do that, no. Do you think it would have affected it?
It may, depending on what fasteners you use. If you would have said nails, I would have cringed. I build a lot, as Mr. Schmidt knows, I build a lot of docks on the boathouses. And depending on what fastener you use and what your spacing is, it can add to how much pounds or flex you will get on.
Oh, sure.
You'll have to go before they're good for, but this would not be bad.
Yeah, did you compare, what was the actual weight versus your design weight? Did you look at that?
I was not able to measure the bridges themselves, I didn't know.
Okay. And then, well, do you have any idea why, besides not necessarily being a structural engineer, as to why the actual is a little bit more than design?
I think it could have been maybe that the wood was like really wet. We had to, actually while I was screwing a lot of the deck boards, like it was obviously very wet. So I don't know if that could have affected it. It was off by, I think about, I don't know, it was definitely like a couple 16ths of an inch, pretty much, in difference in deflection. So yeah, so there was a notable difference in deflection, but nothing super dramatic that I think it was anything super flawed in the math. But I think that's why I think it was something like moisture of the wood.
And one other question, how would you say the aesthetic of the bridge affected your engineering of it? Do you think you could have made it better by making it not look as nice?
I don't think so. It wasn't really something I accounted for while building it, but I don't think so, no. Maybe if I made it a little bit shorter, I could have saved a little more weight, but then I think at some point you'd run into a problem with just getting anything across it.
Sure. Stiffness, yeah.
Yeah. Yes.
If you were to do something similar in the future, what would you do differently?
Well, I definitely save a lot of time drafting it, because there's a very big difference between this and the first draft. So just knowing that I have to, just knowing how to space things, or just how to distribute the load, a lot nicer would have been better. Different. I might have looked at some different materials other than just wood or steel. I looked at decking as well, like some composite decking, but it's just a lot more expensive and it was a lot heavier generally. So I don't know what other materials I would have looked at, but maybe there's no solution to in the first place, but I'm not sure.
What was your favorite part of the entire project?
It was either the construction is that all the work actually paid off in the end. It was kind of fun just building it. Otherwise, guessing and checking on a lot of the math where you put a number into the equation, it should equal this, but it doesn't, and I have to go back like 3 different equations with 3 different cells and find out why it didn't take the right number. And then just figuring out the entire spreadsheet was really fun.
Did you enjoy working with your dad?
I did. He was a big help, yeah. Especially with a lot of the spreadsheet stuff, having him to check over everything and or give more detailed explanations, especially to the shear and bending strength and just the different parts of that.
Did you consider spacing the decking out a little bit more to reduce weight? Being that a four-wheeler doesn't need a tight seam? Was that more aesthetics?
It was more aesthetic, so actually that just kind of go back to his question, but yeah, I did not consider that, but in hindsight, yeah, I probably would have saved, I mean, I'm sure a decent amount, or a couple boards at least, decent amount of boards, so probably would have cut down weight. Yeah. Any other questions?
What would you say was the most demanding thing to learn fresh out of everything? Like you said, you had a foundation in the algebras and the CADs and the physics and so on. What was the biggest gap you found as you went into this project?
I think it was definitely the units. So especially with like the loads, I've never heard of pounds per linear foot before. So just going through the process of
The majority of the lingo, basically.
yeah, pretty much, and like figuring out why certain or like converting even between like feet and inches, like what I had to do to like the top of an equation to make sure it equaled on both sides. The units, so pretty much the units and how they converted from each equation. Yeah.
You guys good back there?
Yo.
Your peanut gallery seems happy. Anything else from the panel?
I got a comment. It was incredible to see someone of your age be able to present on a topic that's probably one of the hardest for engineers to learn. Wood is a very complicated design, and there's a lot of modification factors that go into it, and it's really hard to wrap your head around it, especially reading through the NDS manual and finding your lumbers and the information within there, trying to figure out where it goes. It's very complicated, so it's very impressive that you were able to do that, and you spoke very clearly and it seemed like you really understood what you're doing, so that was very impressive.
You're here. Well done.